Howdy folks, welcome back to another CS 120 honors lecture. In today's lecture, we're going to be reviewing ownership and going into borrowing and dereferencing in Rust. So like I said, we're going to review ownership and then review the copy and clone traits that Arul talked about last lecture. Then we're going to introduce borrowing and how dereferencing plays into borrowing. So you might be familiar with dereferencing pointers in C++ or C. So we'll talk about how dereferencing plays into Rust and Rust's borrowing and ownership system. And at the end, we're going to talk about borrowing and how that plays in with data structures, specifically vectors, but this can be applied more generally to all types of containers. Okay, a couple quick course announcements. So homework 4 is releasing today. It is due on the 16th at midnight. MP0 is due next week on Wednesday at midnight. MP1 is going to be releasing next Monday, and it'll be due 2 weeks from next Monday. These are, of course, the 100% credit deadlines. The 70% credit deadlines are a week after these dates. Okay, so let's get into some ownership. So if you recall from the last lecture, we have these 3 rules of ownership. So each value in Rust has a variable, and that variable is called its owner. And there can be only one owner of some piece of data at a time. And when the owner goes out of scope, the value will be dropped. So I should say, this is the one thing that I ask you to memorize. I'm sure this may come up in an interview question if you're interviewing for Rust. Know these 3 rules, memorize them by heart. Obviously, you need to know what they mean, how they apply to Rust, but if you take away anything from this class, this is the main point of the ownership model. So be mindful to these 3 rules and how they play into Rust. Okay, so we have this variable s here. S owns this piece of data, hello. It owns this string. And then we enter this new block of scope. We're entering this new curly brace code block. We have this other variable w. W owns this string world. So then we can do something with w. But once this scope lock, once w goes out of scope, this data is dropped. So nothing else can refer to it. Nothing else can own it. And at the end of the function, s is also dropped. So this piece of data, hello, goes out of scope once s goes out of scope. And so we said that variables or data can only have one owner. So what happens if we try this sneaky little statement here? So we have x owns this string hello. And like in many other languages, you can say just let y equals x. But there's a little bit more nuance in Rust. This line won't compile. Well, this line will compile, but the following line, the print line, this will not compile. You cannot have 2 owners of one piece of data. So we either must say that x owns this data or y owns this piece of data. And so as it happens in Rust, when you say this let y equals x, y becomes the new owner of this string. So x no longer owns a piece of data, x goes out of scope. X is no longer a valid variable if you're saying let y equals x. So if we tried to uncomment this line, print ln x, our code would not compile. But since y is a valid owner, it's a valid variable, we're able to print out y. So remember, there can only be one owner at a time of some piece of data. And so today's lecture will talk about how we can sort of get around this when we want to have multiple variables sort of referring to the same thing. Okay, and we talked about copy and clone in the last lecture. So copy is this trait that's automatically defined for primitive types, so integers, floats, booleans, characters, etc. When you have this statement let y equals x, the data is copied into a new sort of location in memory. So you have 2 identical pieces of data, and so one variable owns the original piece of data, the other variable owns this new copied piece of data. So copying is automatic for primitive types, which is why you're allowed to say this let y equals x, because x is a primitive type. And so we can change x, change y as we want, and our code will still compile. It will work because when we do this let y equals x on a primitive type, we're creating a separate copy, a separate piece of data. So that's the implicit part. That's a little sneaky bit. So watch out for that. And so when we say clone is an explicit function call. So we have to say .clone to make a deep copy of some data. So you're saying that my data might potentially be large. It might potentially be hundreds of thousands of bytes. And I'm intentionally saying I want to copy that. Rust will never assume that you want to copy a large piece of data. You have to actually tell it to with the clone function. So like we said, clone is this explicit function call. So when we try to say, create a new string, x on this string hello, and then we're saying move ownership from x to y, we no longer have access, or rather x no longer has access to that piece of data. So this line of code will not compile because we moved ownership of this string into y. So we're no longer able to use x to get out of that piece of data. So if you see this compiler error, borrow of moved value, you have an ownership error. And usually the compiler is good enough to tell you that the value was moved out of a variable at some line of code, and you're trying to move it at a different, or you're trying to use the moved value at a different line of code. So that's invalid. But like we said, strings are, can be large pieces of data, but in this case, we do want to copy it. So we're telling Rust, please make a copy of this piece of data for us, make a deep copy. And so we can go on and use both pieces of data. So x refers to this original piece of data. Y is a deep copy of the data somewhere else in memory. And we'll talk about what memory actually looks like in code in 2 future lectures. But sort of keep in mind that we have these variables, but also the pieces of data that are located somewhere in your computer's RAM. And we use these variables as little references to individual pieces of data. Okay. So we were talking about this in a previous slide. Values can only have one owner. And so we're no longer able to use x. We're no longer able to use x to refer to that original piece of data if we've moved ownership out of x. And so we're able to fix this in Rust with this thing called borrowing. Jumping ahead of myself. We can fix this issue by, cloning the data. We're making this expensive operation to look at the string, to look at all of the characters in it, and move them to a different piece of, different location in memory. So you have 2 identical pieces of data, and this can be a costly operation at times, especially if your string is thousands and thousands of bytes long. So sometimes we want to be able to refer to the original piece of data and not make a deep copy. But also give us like this 2 different variables referring to the same thing that you get in other programming languages. So we're looking for a way to avoid cloning every single time we want to have 2 variables referring to the same piece of data. Okay. So we also talked about how you move ownership of variables when you pass them as arguments to functions. So we have this variable class. Class owns this string, and we're moving ownership from class to name. This is a little bit implicit, but when you pass in class into say hello, class moves ownership into name, and then name gets printed out, and name goes out of scope at the end of this function. So this piece of data is dropped. And so we're no longer able to reuse it if we want to say call a different function, call the same function again. So that brings up a problem. We want to be able to pass data into functions multiple times. So again, we want to have a way to have multiple variables refer to the original piece of data. So this is where Rust's references come in. So you've probably seen this in some of our assignments in the past. You've seen this ampersand symbol, and so an ampersand symbol represents a reference, similar to C++. References allow you to refer to some value without taking ownership of it. This comes at a cost. References are not as powerful as owning the piece of data, but they allow you to refer to it, to read it. So we call the action of creating a reference borrowing. So when you have this ampersand in front of a variable, you are borrowing the data that that variable owns. Okay, so there are some restrictions to borrowing. At any given time, you can have either one mutable reference. So you can have this reference to an original piece of data, and you can use this reference to modify the original data. That's extremely powerful. But similar to how each piece of data has one owner, we're only allowed to have one mutable reference to the original data. So very, very restrictive if you want to change the original data. But we can have an infinite number of immutable references. So if we want to just read the data, we can take as many immutable references as we want. So we can have a bunch of different function calls that simply read the piece of data and move on. So borrowing comes with these restrictions. If you want to change the data, you can only have one reference, so the owner and then the other immutable or the mutable reference, or you can have the owner and an infinite number of these read-only references. Okay. So I should point out the owner, the variable that owns the piece of data, should be mutable if you want to take a mutable reference. And this makes sense. If we declare a variable as immutable, like we're not allowed to change it, why should a reference be able to change it? So if you want to take a mutable reference, the original data must be mutable. Okay. And like these slides point out, you take a mutable reference with the ampersand MUT keyword, and you take an immutable reference with simply just the ampersand. And you cannot make a mutable reference to an immutable variable because that sort of violates our definition of mutability. Okay. The other rule is references must always be valid. So you might have done this in C++ where you're taking a reference to some stack data and you're using it somewhere in your program, and then suddenly you leave your function call and you get garbage data. So C++ allows you to take garbage references. I mean, albeit you can put restrictions on it, you can add compiler checks and all that, but you're allowed to take a garbage reference in C++. Rust restricts that. So references must always be made to variables that are in scope, and references can only last as long as that variable is in scope. So this alludes to this concept in Rust called lifetimes. We might be covering it in a special topics lecture, so don't worry too much about it yet. This will come up in MP3, and we'll touch briefly on that later, but references can only be made to variables that are in scope. So make sure that your variable is in scope when you want to take a reference to it. Okay. So this example just sort of drives home the point that you cannot take multiple mutable references to a variable. So we have this variable x, it is mutable, we can take a mutable reference of it. X owns this piece of data, hello. And so when we say y equals ampersand mut x, we're saying y is a mutable reference to our variable x here. It refers to this data, and so we can use y to change the original piece of data. Okay, let me briefly hide my camera. So we see this error here because we can't take two mutable references to our data. So this is a little bit tricky, but we know y is a mutable reference. But when you're calling a function on x, when you're saying push string, this function is also trying to take a mutable reference to your data. It's trying to mutate the original data, push some characters onto it. So therein lies the problem. We have we're trying to take two mutable references, and this is illegal. You'll get a compile error here. This function call is trying to take a second mutable reference to x, and so this will not compile. Okay. So let's fix our example from earlier using what we know about borrowing now. So we have this variable class owns this string, and we're trying to pass class into this function, say hello takes a string and prints it out. So when we do, name takes ownership from the variable class. So now name has ownership of our string. We print out name. And finally, name is dropped at the end of the function. So our data is no longer, or our data is dropped as well. So we're no longer able to use our data and try and call say hello again. Luckily, we know that we can take references to it. So we know that all we're trying to do in say hello is print it out. We're not trying to change the original string. So I made this function here, say hello borrow. The only difference is we're borrowing this piece of data. We're not taking ownership of it. And all we want to do is read it. So we're going to, print out the name, print out the original piece of data. But when we drop name, when name goes out of scope, we're not dropping the original piece of data, we're just dropping the reference. And dropping the reference, just nothing happens to the original piece of data. The reference is separate from that data. So if we change the first function call to say hello borrow, take a borrow of class, we do that with the ampersand symbol, our code now compiles. So there we go. So we take a borrow to this piece of data, print it out. This say hello will take ownership and drop that piece of data at the end. But we don't care because we're no longer using the original piece of data. Okay. So we can fix this issue of wanting to pass around pieces of data to functions that only read the data with immutable references. Just adding the ampersand in front of the type and adding the ampersand in front of the variable when passing it into a function. Okay. So now I'm going to talk about dereferencing mutable references. This is always a sort of challenging topic in this class. There are certain rules as to when you do need to dereference and when you do not. It's a little tricky. Usually if you need to dereference, the compiler will tell you, but we'll try and lay out a couple sort of common scenarios when you do need to dereference. Okay, so if you don't know what dereferencing is similar to that of pointers in C++. If you want to change the data that a pointer points to, you add in this star in front of the pointer, and you're able to change the data with star pointer equals your new value. So you can mutate the variable that a mutable reference refers to by dereferencing that mutable reference with a star. And so I want to point out references are really just addresses in memory. They're places in your RAM where you have some piece of data and you're just saying, I want to refer to that. And so similar to C++, you can just dereference that reference, dereference that address to change the data or the memory of that address. So if you're comfortable with pointers, you should be comfortable with mutable references, as they are pretty much acting the same way. Okay, so when do you need to dereference something? So when you're using mutable references to primitive types and you want to sort of change them, use their values, whatever, you need to dereference that reference to get access to that piece of data. Similarly, if you're using sort of basic operations on non-primitive types, so you're using the plus sign to add things to strings, you need to dereference that mutable reference to a string. So we'll touch on iterators in the next few slides, but iterators are a sort of way to access every element of a data structure in some order. And so when you're using an iterator that can change the data inside a vector or change the data inside a hash map or whatever other data structure you're using, you need to dereference the reference that an iterator gives you. I have a slide on this in a couple slides and you'll see what I mean. But when you're using mutable iterators, you need to dereference. You do not need to dereference when you're using this bracket access notation on vectors. When you're using the bracket and then the index, you don't need to dereference. Rust does that for you. So if you have a vector, myvec, and you're trying to access the data at index I, you do not need to dereference here. And custom types like strings handle the dereferencing for you when you call methods on those mutable references. And Arul will touch on this in, I believe, next Thursday's lecture when he talks about creating custom types. But custom types have a built-in feature to sort of handle this dereferencing for you. Yeah. Okay, so let's do a brief demo on dereferencing. Okay, so I have two variables here. I have a string, CS128 honors, and a integer, 128. Then I have a couple functions here. So I have hello that takes in a mutable reference to a string, greet that takes in a mutable reference to a string as well, and increment that takes in a mutable reference to an integer. Okay, so hello simply just takes the string, dereferences it, and then sets it equal to hello plus the original string plus an exclamation mark. So I want to point out we have this custom type here, and we want to change the data inside, so we're going to dereference that. Greet also changes the original data. It just adds to it, but we're not calling a dereference here because we're using this function call. This function call will do the dereferencing for us and add this string to the end of it. Okay, and then when we're doing this mutable reference to a primitive type to an integer, we need to dereference it if we want to increment it. I should also point out that if we want to just say x equals x plus 1, we'll get this error here. So plus cannot be used on an integer. You can dereference it with a star. So the Rust compiler is pretty good about telling you when you need to dereference. In this case, it is telling us to. Cannot add an integer to a mutable reference. You have to dereference this. So yeah. So after the first function call, we should get hello CS128 honors. After the second one, we should get hello CS128 honors. It's nice to meet you. And finally, this little sequence here should print out 129 and then 130. There we go. So, dereference primitive types. Look at what the compiler errors tell you. You saw in that case it was really helpful in telling us that we needed to dereference this. So, trust the compiler messages, sort of learn to decipher them. They're very, very helpful. In this case, they tell us how to fix it. So now we're going to briefly touch on ownership in vectors, and this will also apply to other data structures like hash maps. I believe you'll also be using hash sets in MP2 and then hash maps in MP3. So the ideas for vectors also apply to those data structures. Okay, remember, values can only ever have one owner. So what happens when you add an element to a vector, or any other data structure for that matter? The data structure owns that value. So you can't move ownership from out of that data structure unless you remove the data from your structure. So when we try to access a value from a vector, we need to take a reference to it. We're not able to simply, directly take ownership of data out of a vector because the vector needs to keep ownership of that. It needs to keep it in its ordered list of elements. So we can't simply just move it out of the vector. So when we try here, we have this vector of strings, and we're trying to get element at the index 2. We get a compiler error here because we can't move ownership of this element into a new variable. You will be able to with primitive types, though, I should note. If you have a vector of integers, you will be able to use this statement, let element equals x bracket 2, because primitive types do implement the copy trait. You're able to copy primitive types, and so you can have this statement, let y equals x. But in this case, we're trying to move ownership of a string from the vector to the element, and that is not okay. Again, we can fix this by just adding in an ampersand, borrowing that piece of data, and our compiler error goes away. Okay. So I said I would talk about vector iteration. So for loops in Rust, you can do them in a bunch of different ways. My personal favorite is iterators. You can also use the standard for I in range from 0 to something. That's how you do it in Rust, from 0 to the length of the vector, do something. So with iterators, you call this function, so iter mute. There are more options about how to iterate on the next few slides. But you get this variable lm that is a mutable reference to each particular piece of data in the vector. So in the first iteration of the loop, we get a mutable reference to 1. In the next iteration, a mutable reference to 2, and so on and so forth. And so we said in the previous slides, if we have a mutable iterator on a data structure, we need to dereference that mutable reference to each element in order to get the data and in order to change it. So in this case, we're dereferencing the element and adding 2 to it, then multiplying it by 128, and then replacing this piece of data with the result. You can do the same thing with bracket notation, something you might be familiar with from many other programming languages. For each index from 0 to the vector length exclusive, get the element of the vector at index I and change it to this. So these two are equivalent. I should note that if you want to do this, if you want to change the data, you need to have this mute keyword in here. If you want to call iter mute, you also need to have this mute keyword here. So anytime you want to modify your data structure, the data structure has to be mutable. Okay, let's briefly show that. So we have this vector here. We're going to iterate over it, add 2 to each element and multiply by 128. And then in our next loop, we're just going to add 1 to every element. And finally, we're going to sum up every element and print that out. So this dot iter is another way to iterate over vectors. As you can see, what my VS Code here is telling me, iter just gives me immutable references to each element. I get just a unchangeable borrow. Iter mute, contrastingly, gives me a mutable reference. So use each method based on what you want to do. So there we go. Add 2, multiply by 128, that gets us this first line. Add 1 to every element, that gets us the second line, and summing up every element gets us this value. Okay, running a little tight on time here. So I'm just going to briefly run through these. These are some helpful methods that you can use on vectors. You can just refer to these in the slides. You'll be using these on MP1. So bracket notation, try and take ownership or copy the value at index I. You're really only going to use this on primitive types. Immutably borrow the value at index I, use an ampersand. Mutably borrow, ampersand mute, and the vector must be declared as mutable. There are functions that accomplish the same thing, but they return an option. So .get gets you an immutable reference. If I is out of range of the index or of the vector, if it's an index that's not valid, it will give you the none type. If you try to use an invalid index here, your program will crash. It will panic. So the option is the safer bet, but if you are 100% sure that your index is in range, you can just use this bracket. Get mute, same thing, just for an option to a mutable reference. Okay, and then we have these iteration methods. So .iter gives you immutable references, iter mute gives you mutable references, and the one we did not cover, into iter. So you're going to take ownership of the vector, take ownership of all the values in the vector, and iterate through them. Quick warning though, you can no longer use the vector after you call this method. So be careful, if you use into iter, you're taking ownership, but you no longer have access to the data after the loop ends. Okay. These will be on the slides, so you can refer to these later. That was just a quick run through because we are at the 30-minute mark. But yeah, thanks folks. Thanks for hanging in there. I'll see you all next week.